Let us start section 4.2. Solutions, or maybe I'll say solving. Systems of linear equations using the substitution method. So last time we looked at systems of linear equations, and we looked at solving them using the graphing technique. Now the graphing technique was really not very practical, and so let me give you a technique that is actually uh, useful in solving systems of linear equations. And so let me do problem number 4 on page 157. In exercises 1 through 30, solve the system of equations using the substitution method. So the first technique that I'm going to be introducing is the substitution method. And so x equals 2 plus y, and let's say 2x plus 3y equals 4. Let's call this equation 1, and let's call this equation 2. Okay. And so the idea of the substitution method is that we're going to pick one of the equations and solve one of these equations for one of the variables. And so I will look for the equation that's easiest to solve for one of the variables. Well, obviously, if I look at equation 1, it's easiest to solve equation R1 for the variable x because, well, it's already been done. And so x is equal to 2 plus y. Maybe I'll call that equation S1. And so now that I've solved one of the equations for one of the variables, I will substitute that variable into the other equation that we have not used. So it's very important to substitute into equations that have not been used. And so I used equation R1, so I will not substitute into R1, I will substitute into R2. So I will use equation S1 to substitute for x into the equation R2. So I have not used R2, so I will substitute in this case for x into R2. And so let me substitute S1 into R2. And so I get 2x. Well, I'll substitute for x 2 plus y, because I said that x is equal to 2 plus y, by equation S1 plus 3y equals 4. Okay, so now let me simplify this. So let me multiply the 2 inside the parentheses. So by distributive property, I have 4 plus 4y plus 3y equals 4. Four plus 2y plus 3y equals 4. Let me combine like terms. 2y plus 3y is 5y. And so 4 plus 5y is equal to 4. Let me subtract 4 from both sides of my equation. So by the additive property of equality, I have that 5y is equal to 0. Now that I've isolated y on one side of my equation, let me divide both sides of my equation by 5. So by the multiplicative property of equality, I have that y is equal to 0 divided by 5, which is 0. Let me call this, let's say, S2. So I now have that y is equal to 0. Now let's use this y to substitute into my S1, and that will then determine what my other variable x is. And so I'll use S2 to substitute for y into the equation S1 to solve for x. Okay, and so now I will use S2 to substitute into S1. And so S1 says x is equal to 2 plus y, but y is 0. And so I have that x is equal to 2 plus 0, which is 2. Therefore, the solution to my equation is x is equal to 2, y is equal to 0. And that is a solution to my system of equations. And so this is a nicer technique than the technique that we had from before, the graphing technique. There's no sort of guessing where the lines intersect. There's no having to reach, well, you should check to see that the solution actually is valid, especially if you are doing this on an exam. This is one solution, so this is actually a consistent system of linear equations. And well, since there's one solution, this is actually a pair of intersecting lines. Okay. Let me do problem number 30. So R1 is 3y is equal to x minus 6. R2 is x minus 3y is equal to 6. Okay, so let's do this. So let's solve. Oh, let's see. I guess I'll do that. Solve for y in R1. Okay, so let's do R1. I want to solve for y, so I have 3y is equal to x minus 6. So let me divide both sides of my equation by 3. And so I get that y is equal to 1/3 x minus 6 divided by 3 is 2. I guess I'll call that S1. Okay. Now let's substitute S1 for y into R2 because we used R1. And so I'll do S1 and I'll go into R2. And so I have here, wherever I see a y, I'll replace y by 1/3 x minus 2. And so now, let me multiply 3 inside the parentheses. So I get here x. 3 divided by 3 is 1, times x is x. Negative times negative is positive. 3 times 2 is 6, equals 6. So now, the x's cancel. So I get 6 equals 6. Well, now I've eliminated all my x's, all my y's. I don't have any variables to solve for. So when that comes up, either we're going to have an inconsistent system or a dependent system. And I've got to determine which one it is. So either we're going to have two lines that are parallel or two lines that are coincident. And so somehow the slopes, so this sort of says the slopes are the same. Okay, so slopes are the same. And now I've got to determine, is this going to be a pair of parallel lines, or is this going to be two lines that are coincident? So first off, is 6 equal to 6? Yes. So that's a true statement. If that's a true statement, then this is a dependent system. So it's a dependent system of linear equations. This is the case of coincident lines. These two equations were the same equation. And so I have two lines, but they're actually the same line. It turns out that there is an infinite number of solutions. For this system of linear equations. Well, let's figure out what it is. Well, I can either say that the solution is, well, any of the equations, either R1 or R2, because they're both the same equation. So I could just say R2 is the solution. It's all ordered pairs which solve that line. Or if I want to write it as a system of, say, a one-parameter family solutions, I can do the following. I could say, well, let's say y equal t. Then x minus 3y, which is t, is equal to 6. So x minus 3y is 6. Add 3t to both sides of my equation. And so I have that x is equal to 3t plus 6. And so if I want to write this instead of an equation, so this is a solution, but written as an equation, let's write it as a set of ordered pairs. And so it's just x, 3t plus x, comma y, which we call t. So it's x, 3t plus x, comma y, which is t. This is true for all real numbers t. And this is my solution written as a one parameter family of solution. So this is actually the preferred way of writing your equation, your solution to your system of equations as some sort of ordered pair. But again, you could have written it just as an equation. Let me do problem number 54. So I have here R1, 2x minus y minus 3.7 equals 0. R2, y minus 5x equals negative 11.2. Let's solve. So the first thing I have to determine is which of these equations is easiest to solve for one of the variables. In this case, since there's only one thing I'd have to do, I guess, solving for y here is actually the easiest. Notice there's a variable of 1, there's a constant of 1 in front of a variable. And so it's easiest to solve for that variable. So let's solve for y in R2. So R2, let's solve R2 for y. And so I have y minus 5x equals a negative 11.2. Let's add 5x to both sides of my equation. So y is equal to 5x minus 11.2. Let's call that S1. And now let's use S1 to substitute for y into, well, we used R2, so R1. So I have to check to see which equation we had used previously. Please note, if you accidentally substitute into the wrong equation, say you substitute back into the same equation, what will happen is you'll actually come up with the same situation that we got in the above system, where you'll have some number equals another number. And so you have to be careful that you didn't substitute back into the original equation, because you might be falsely led into thinking you have a dependent system, in which case it isn't a dependent system. It's just that you have solved your system incorrectly. Okay, so let's substitute S1 into R1. And so I have 2x minus y, 5x minus 11.2 minus 3.7 equals 0. Okay, so I have 2x. Let's distribute the negative sign inside the parentheses. And so all the signs inside the parentheses will change. So it'll be a minus 5x plus 11.2 minus 3.7 equals 0. 2x minus 5x is negative 3x. 11.2 minus 3.7 is 7.5. Let me subtract 7.5 from both sides of my equation. So I get negative 3x equals negative 7.5. Let me divide both sides of my equation by negative 3. So x is equal to negative divided by negative is positive. 7.5 divided by 3 is 2.5. Maybe I'll call that S2. Now let me use S2 to substitute for x into S1 to determine my other variable y. So I'll do S2 and substitute into S1. Okay, so I have here S1 is y equals 5x, which is 2.5 by S2, minus 11.2. Okay, so now let's simplify this. So y is equal to 12.5 minus 11.2. Y is equal to 1.3. And so my solution is the set of ordered pairs, the ordered pair 2.5, 1.3. Notice that these are intersecting lines. Because I've been able to solve for y, this is just intersecting lines. These are coincident lines. This is a consistent system. And so this has only one solution. Actually, that was about, actually maybe I'll do this. Okay, so that really finishes off, section good. That really finishes off section 11.2. Let me go on to